let us continue with the topic that we started with yesterday. And we were at this point in the last round, right? So from this point, we will continue. And for that, I can put it on a larger size. Yes. So automation in factories actually started very early in the 20th century. Okay? So that is the starting point of automation as such. But robotics is not automation, or all automation is not robotics. And after that, automation progressed as usual. By 1945, telemanipulation had started. Okay? So it is like uh, manipulation of objects from a faraway, safe location. And that was very important because in order to process nuclear material, which came up to industrial proportions at this stage, okay, it was useful. After the war, after the Second World War, research continued and servo-controlled telemanipulator started operating. Earlier, telemanipulation was very mechanical control, and actually one very crude way of doing it is to use mechanical linkage between a manipulator at the site and a replica of it at a safe location away from it, and through these mechanical coupling you move the master manipulator here in the safe place, and the slave manipulator at the site executes the operation by copying it. Okay? So this was the original kind of manipulation. It is called master-slave manipulation. Okay? Servo-controlled manipulation, actually master-slave manipulation is still useful because for precise adjustments, you may do it by hand, okay, with your judgment, and the copy is produced there. The servo-controlled telemanipulation, that is automatic control, started in 1948. After a few years, numeric control machines started for manufacturing. Okay. And then in 1954, first time a robot was designed, which was programmable, in which you could change the program. You would note that roughly this kind of period was also the period in which the first faltering steps in computer technology was being taken. Okay. And after this, the development and packaging and marketing installation of robots was a matter of sort of expectation. Okay. So the first robot was installed in 1961. And within that decade, robotics as a discipline in technology emerged in the worldwide arena. Okay. Leader was, of course, USA, and Russia and some European countries also a little in the field. Japan soon joined. Okay, so during the phase of development from this point, 1950s to now, 2020s, you can say, the trend of the jargon of the field also has changed somewhat. By the focus, by the change of focus of the what aspect of a robot people think of. Okay, so originally, since it came from science fiction, so the original projection of robots were extremely intelligent, almost paralleling humans, and so on. And at the time, the emphasis, the thinking manner was on the brain, okay, the logic of it. And that is why for the original word cybernetics, okay, so originally the field of robotics was known more as cybernetics, okay, which operates with intelligent computational action. Okay. Cybernetics is actually related to computer science, basically. So the focus was on logic, on brain, on intelligence. However, soon it was found that the main task that is to be done by robots, that is primarily mechanical, and a lot of it can be done mechanically. And for that matter, uh, the troubles that mechanical engineering also offered to solve to people, okay, kinematics, dynamics, and then uh, stresses, strains, deformations, all sorts of things come up from mechanical engineering side also. They are the big issues to be handled, and the intelligence issues were very little handled, and for the rest, the dream of humankind was enormous, but a very less part of it could be actually accomplished really. Okay, so slowly the focus shifted from the intelligent logic to mechanical work, and then the word related to mechanical work came into picture. Now the field was known as robotics. So during 80s, 90s, and even the part of the first decade of this century, it was mostly known as robotics. But slowly, people started talking about robotics being an interdisciplinary area through the confluence of not only mechanical engineering and computer science, but also electrical engineering and electronics. And electronic hardware was seen as one of the big issues in it. Okay. And now the world has again changed from its physical labor focus to a joint focus of mechanical engineering, mechanics, and electronics. And now it is often called mechatronics. So in the third floor of Northern Lab, we have a center for mechatronics. When I joined this institute, it was called Center for Robotics. So mechatronics is the meeting point of mechanical work with electronics. So that is the sense. Okay. Now, the robotic system. Now, at this stage, I will point out to you that the conceptual background that I am trying to give you, that kind of a conceptual background essay, you find in the first chapter of the textbook. Break. Okay. And early chapters, one and two of Crafter, give you a lot of details about these things. Okay. So components of a robot, how the robot morphology is organized, okay? What are the coordinate frames and so on. Coordinate frames in another context we will come across in the proper lesson also. So how the robot looks, how the robot is constructed, this is about one part and so on. So this part you get in the early chapters of Crafter also. So these things you should read thoroughly, one round. I mean, one round, most of the things you will get. And you need to get in your head the pictures that emerge from these pages. Okay. So that will be reasonable understanding. And those who like it a lot, they can read it again and again. But for a realistic picture, once at least you must read chapters, early chapters. Okay. So robotic systems. First of all, um, what does a robot have? What does it consist of? Like a worker, it has its typical elements, mechanical structure, it must have the manipulator, which is analogous to our arm, which typically arm we work. Then it has a controller, which takes care that it is going according to the plan. It is moving according to the plan. That is analogous to our brain. Then how does it know whether it is going according to plan that or whether it has to be corrected? So where it is supposed to go, what it is supposed to do, that is already there in the plan, that is known. And where it has actually gone at any instant and what it is actually doing at any instant. So for knowing that, it needs sensors. The way we use eyes, ears, skin, okay, and then whatever forces it has to apply, for that it needs actuators. Whether it is motors or linear actuators, hydraulic, pneumatic, or whatever it is, but some sort of actuators, some power source, which is analogous to our muscles. With this much, work hopefully can be accomplished. Okay? So that is what is done by our bodies and by robots also. There are a few systems which are not exactly robots, but quite close by in the sense that a lot of commonalities are found in those systems, those engineering systems and robots. For example, hard automation follows to a good extent the same structure of operations which a robotic automation might. Okay, so but it is not reprogrammable. That is why it is called hard. This automation cannot be changed by you know next week or something like that. So it is not that you do not use program B, use program G, and then the system starts doing a different work. That is not possible in hard automation. In robotic automation, in principle, it is. You have to have the alternative program. Okay. Manipulators are also not treated very much at par with robots, though many times people talk about robots. NC machines are not robots; they are just single program. Of course, they can be multi-programmed. I mean, differently programmed, it will cut along a different curve. Okay, but they are not really classified as robots. Automated guided vehicles, a lot of their theory and operations are similar to robots, but these are basically vehicles. For example, in a car, if you make it programmable and you don't need the driver anymore, then it is actually an automated guided vehicle. Okay? And literally, it will be. Walking machines. Walking machines are not just robots. Okay, they are machines. Now, with the walking machine, if you put an arm assembled into it, with which it does some useful service. For example, it takes your thermometer and goes and shows it to the doctor, and then from the doctor it takes the medicine and brings and gives it to you. Okay, then you would call it a walking robot. Okay, actually, multifunction toys are sometimes very close to robots. A lot of its operational details resemble. So, what is a robot and what is not a robot? This question also will arise, and sometimes there will be a few things which will fall close to the boundary line. Okay, so that can happen. So typically, you try to call a machine robot if it does some active task and it displays sufficient generality and autonomy. So unless it is autonomous enough, you do not call it a robot. On the other hand, unless it is general enough, a very particular thing in the same trajectory, if it goes every time and does a repetitive thing all the time with no variation and cannot take any variation, then typically you would not call it a robot. What are the typical applications of robotics? In the industrial sector, typically there are many other possibilities. of work done by robots, but mostly these are the tasks which have been done with robotic automation, which are very common and repetitive, and rules are simple: welding, spray painting, material handling. That is, taking things from one location to another location and delivering at a precise point. Assembly is actually a difficult task for a robot, but it has been done to an extent and expanding. Inspection is another important work. For example, products that you have made, if you can describe how the correct product should be, then by matching product to the template, you can try to find out which products are fine and which ones are not all right. Mining is another operation for which industrial robots have been used. In strategic sectors, robots find good use: nuclear, space, unsafe for human beings. So repetitive, laborious, or unsafe. These are the typical zones in which you prefer to deploy robots than human beings. Underwater, demining. Now you see, mining is one thing, demining is another. This is actually related to defense. Mining is to get copper, nickel, iron from the mine. Okay. Demining is to remove mines which are actually bombs, which you put in the enemy location or on the way of the enemy so that they cannot come and attack you easily. Okay. So after the war is over, then you have to, perhaps you have captured that land some way, and then you have to get rid of those mines so that they don't burst accidentally. So this operation is called demining. For that, rather than sending human beings, you would like to send robots, which will you can remove the mines or uh, destroy them safely. Reconnaissance and surveillance. So this is also defense application. So if you can manage scouting territory which is not exactly your territory and maybe even enemy territory, so that for that purpose, reconnaissance and surveillance, you can apply robots. Okay? This is actually done. In the services sector, surgery uses robotics. Prosthesis actually uses something close to robots. I mean, robotic parts. So you try to remove the hip of somebody. You may try to put a complete prosthetic armory for somebody. Okay, so from inside, whatever the subject then tries to accomplish, his intentions, his motions and forces need to be operated outside. Okay, sometimes perhaps with amplification. Entertainment is another area in which robots have been used. Actually, I should have included one more, which is going to be prominent in perhaps coming time, and that is care. Okay, care of old people and patients or housework. So these things also robots can be utilized, and people are talking about them. In fact, a few years back, I saw in the newspaper that a company in Gurgaon is um, marketing a robot called Milagro, Milagro, for housework, okay, for dusting and mopping kind of thing, the sweeping and mopping kind of thing. Basically, it was perhaps cleaning by vacuum or some such thing. So for that kind of thing also, housework also, you can actually apply robots. And if you can get the upper middle class Indians to buy it, when you produce and supply it, you might actually make a good bit of money. Okay. Now we start talking about a little out of the way robots. What are the normal robots I should have shown you, but I have just told you that a normal typical industrial robot looks like a human arm morphologically, and there are extra things. So some kinds of robots have more degrees of freedom than necessary. Okay. This can give you enhanced dexterity, obstacle avoidance, singularity avoidance, and you can do a task better. So these are typical uses of robots with larger number of degrees of freedom. Something like this. With three links, it will be difficult to reach this point A if the base of the robot is outside. But you can enhance the number of links so that it can go around this and reach. So this is actually a good research area. Maybe some of you might work later. With links, you can certainly reach. You have to make the link sizes appropriately, and the design is also a little challenging. And this may not be the only point. There may be several such points where you want the robot hand to reach. Okay. Now, most of the time we talk of robots, we think of robot manipulators made of rigid links. Now, rigid in what sense? Rigid in the sense that during operations, whatever deformations take place, they are extremely small from a practical standpoint. Now, the thing is, why do we make them rigid? So one is ease of modeling. Rigid body dynamics is easier to analyze compared to flexible links. And other thing is that positioning precision is better with rigid links. So, for example, if the um, task is uh, if the task is here, if the task is here, then by having a flexible link, it can swing a little, and then positioning precision will go off. Or even if it sags with higher load, then positioning precision will get damaged. So there is a relationship between the task and the joint motion. Okay, this is purely kinematics. And then in order to give appropriate joint motion against the resistance, you have to give actuation. This is force to motion relation. Now, if you have a flexible link, then what will happen? That based on the task, the entire structures, kinematics, dynamics, the whole thing together, you have to analyze and work out what actuation at this end should be given so that at the other end, appropriate motion is found. And that is cumbersome. So this is one thing. So modeling is one problem, and the positioning precision may suffer. However, if you can now the process this the rigidity actually incurs a cost also in the robotic operation. It's the whole manipulator becomes heavy because in order to be rigid, the links have to be fat. Most of the robots that you will see has really thoroughly fat bodies. Okay, and they're quite heavy. Okay, most of them are quite heavy. So the structure is bulky, and high power actuators you will need. And there are other issues also. So, for example, the dynamic performance actually gets affected with too heavy bodies. Okay. Now, one possibility is to have flexible links wherever you can manage. So that gives you a big area of flexible robots, flexible link robots. So they can be made flexible and light, and the actuators can be small then because the overall weight will decrease. Basically, we are talking about masses because of a reason which I'll very soon. Energy consumption will be less, and it can be maneuvered easily because the inertia forces will not be high. And flexible robots have a very good application in those fields where it is the inertia forces which are really the dominant ones. And in which sector, in which field, the inertia forces will be dominant? Where there is no gravity or less gravity. And that is why in space robotics, people try to use flexible link robots. And there, the modeling actually has to take care of the deformations also along with the other things, normal kinematics, dynamics. So with that, the deformation also has to be done. So the entire kinematics dynamics gets integrated with the constitutive relations of the solid bodies, making the robot links. So this is very interesting area, and some of you might think of doing some work in this later. Okay. For flexible link robots, there will be challenges. Modeling will incorporate a lot of trouble together, and direct relation will be between task and actuation. Analysis will be difficult. Vibration control will need specific effort, and implementation also will have its own challenges. Another field which has come up in a big way in last 3 decades, that is actually that has been positioned as an antithesis to normal human arm like robotic structures. Okay, so human arm like robotic structures, anthropomorphic structures are the typical classical traditional kind of robotic structures. Okay. And its drawbacks are that it may happen that an overall 20 kg robot is actually carrying something of 5 kg, okay, or even that, if that, okay, 2 kg, so something of that sort. So, or even less. So the stiffness is low, and vibration takes place at high speeds. When you try to start moving at high speed, it will start vibrating. Okay. And positioning precision low because of this bulky structure. So one counter proposal to this was why serial chain? Why anthropomorphic? Why should it be from like human arm? Okay. In which every link operates in a cantilever style. So the shoulder actually supports the whole arm. Then the elbow supports the frontal area of the arm and the hand. The wrist supports the entire hand up to the fingers. Okay. So each link is actually hanging from a base support. Okay. And that base support with the previous link is hanging from the still previous link. Okay. So this actually makes this so bulky. Okay. Now in the real world, there are other systems for supporting loads. Say when you carry a heavy weight, you put a hand here, you put a hand here, and you put the head in between. Maybe you don't do, but somebody who has to carry this big trunk, he has to do something of this sort. Camel's body carrying the load is actually supported in parallel by 4 legs. Okay. While writing, you use 3 fingers in parallel. Okay, so like this. Now, this is exactly not in league with other examples, but when you do a task like hammering a nail, okay, so you do half the positioning from this side and half the positioning from this side, okay, and positioning means putting it at a position and supporting the load also, okay, and actually you are using 2 arms. You are using cooperation between the two arms. And when they close, you get a closed loop, not simply open chain like ordinary robots. So this gave rise to the concept of parallel manipulators, parallel activated manipulators, or closed loop manipulators, and they became a popular research area in 1990s, and then after that they have continued. So these motivations were these, and these are the challenges. Quite a bit of these challenges actually have been solved in the last 3 decades. But around 1990s, it was a very open field, and a lot of problems were open. How to do it, whether somebody will do it, kind of thing. Then there is another area of modular robots in which it is possible to transport constituent parts and have them shaped, organized in such a manner that at the site they organize themselves and assemble themselves. These are called modular robots. I mean, some people have used very interesting ideas to develop modular robots, okay. And they can be actually used to, um, you know, used to do some operations at a location where the robot needs to travel through a narrow passage. Micromanipulators are manipulators which are of microscopic size. Now, actually, people are talking about nano robots also. Okay. And a lot of science and technology goes deep inside it. Biomechanics and biomedical engineering is another very interesting, very important field of robotics now, and they are emerging quite actively, which helps artificial body parts, helps in making artificial body parts and rehabilitation. Okay. Actually, this has some relation with prosthetics also. Walking machines is another area which has a lot of challenges and takes a lot of um, attracts a lot of researchers. And there are other kinds of mobile robots, mobile vehicles. They are either wheeled or guided. Okay. Walking machines have some advantages over the other because of the terrain or whatever, greater mobility. Okay, terrain independence. These are the typical advantages of walking robots rather or walking machines rather than other kinds of vehicles. How many legs? So 6 legs would be actually easy to control because I mean easy to maintain stability. Minimum 2 legs you will need, which will be extremely difficult. Actually, what we do, human beings do with 2 legs, that is actually quite uh, complicated from the control system perspective. Because 3 legs are actually needed for static stability. Okay. So how do we stand on 2 legs? It is the enormous brain power of human beings which enables humans to do that. Okay. And that is why if you are suddenly afraid or if you are weak, you feel weak at the knees. Okay. So humanoid robot, bipedal locomotion is actually a control challenge. Of course, people have solved it to an extent through several means. And the best possible solution always lies in the future, as always. Now, in the control, of course, in this course, we don't study dynamic and therefore dynamic model-based control. But the idea of dynamic model-based control, which some of you will later perhaps do, is to develop the dynamic model of the system of the robot along with the load and the task, and through that try to give the correct corrective action. Ordinary control, as you will study in this course, tries to um, control the robot along the specified trajectory or along the at the specified position by means of an error correction mechanism. Whatever has been planned and whatever has been reached, if there is any discrepancy between the two, that sensed discrepancy is eliminated slowly. Okay, so that is the typical servo-based control. Now, dynamic model-based control tries to preempt and anticipate what forces will be required at every step, and according to that, give the forces, so that the errors are less to be controlled through the servo mechanism. Adaptive control is another advanced stage of that, in which the dynamics of the robot is also not known completely a priori. As you operate with the robot, the dynamic model of it is slowly adapted. So, based on whatever nominal dynamic model that originally the robot intelligence is aware of, based on that, whatever errors are still taking place, it can sense that, and while correcting it through the servo control, it can slowly try to make small updates in its description of the dynamic model of the robot and thereby adapt the model. That kind of a thing is called adaptive control. So these are actually advanced topics. Robotics we have already talked about. Force control will come in this course itself. So the idea of that is all the objects cannot be positioned in every situation precisely without recourse to the measurement and monitoring of forces. So for example, when you try to hold a delicate object, okay, then you try to not just position your fingers correctly, okay, you sense at the same time what are the reaction of the forces, I mean reaction of the surface between your fingers and object, and if they are in the sufficient zone, then you maintain that force. So that is basically you are trying to do force control. So that is another interesting area. For that, I think some will come in the second half of the course. Sometimes you organize and design your parts and your working environment itself so that through compliance, the required motion takes place more easily. For example, rather than a prismatic hole and a prismatic rod, which would require an enormous positioning precision to put the this precisely at the hole location, otherwise it would not go in. You could make the rod of this shape and similarly the slot also of this shape, so that even if the positioning precision is not very good, even if it gets positioned here, then the surface will actually guide the rod into the hole appropriately. This to an extent you know already. When in total dark, when you try to put your bicycle key in the slot, then you sense even without touching with your finger. Okay, you hold the key here, and if the slot is sitting like this, you can position the key in such a manner that it first heads upward, and then you turn it, and the key goes in. Okay. So this is actually compliance. You are using compliance. Intelligence is another area which is very romanticized. So those who don't know of computers or robots at all, okay, children are completely um, remote location uneducated people. They would, I mean, if stories are told to them, they would feel that robots and computers are so intelligent. They can do this, they can do that, perhaps they can do this, because of outblown imagination. So there are even opinions which differ what is intelligence and whether machine intelligence is at all possible or not. So there have been several models of it. Some of them have been already found not to be of great significance in real intelligence terms. So I take this example that if you program a robot to pick up the hammer and pick up the nails and drive the nails at specific locations, then after reaching the site, if the robot doesn't find the hammer at the proper place, something looking like a hammer, will it be able to do what most human beings, including 7-year-old child, can do? Taking a big rock from close by, one can still hit the nail. Now, you would say that if that idea and that operational ability appears to the robot on its own without specifically training, that if this shape thing called hammer not found, look for some other kind of shape, roughly this weight. If that has not been instructed already, if it is not programmed, even then, will a robot in a situation like that pick up a rock of the proper size and do the task? So, if it could, then you would be convinced of it having intelligence. The way you detect intelligence in a 7-year-old child. So, I mean, these kind of examples can be built where very simple things, actually communication to the robot will require an enormous kind of programming work. So, however, people are telling that you don't know through machine learning where we can reach. Machine learning apparently does not work exactly according to what we understand by deductive logic. Okay. All of that is not else, if not if, if then else kind of thing. So apparently, machine learning can generate its own, I mean, new rules which were never taught, and that has been hoped because some of the games, board games like chess kind of thing, by teaching computers, it turns out that I mean, I have read such reports and stories that the program actually comes up with moves which the original trainer did not think of. So something of that sort may be even possible by logic, though not deductive logic. So rule building, if that can be incorporated in the system itself, then perhaps one day you could get something which is intelligence. We will see. So the apparent intelligence in robots manifests in obstacle avoidance and path planning. For example, if you put a machine to operate and it operates one way, and then you note which way it operated. On that way, if you put some obstructions here and there, and then give the same command to the robot to operate again, and this time if you find that it did not follow its original path, it avoided obstacles and still went and did its task as described, then that would look like intelligence, right? But that is because of good sensing and background planning and the methodology of motion planning that has been already coded in the robot. Okay? So these kind of things are the typical manifestations of whatever intelligence in robots are there. Intelligence to aid to intelligence as usual, sight, sound, touch. Robots have appropriate sensors. These sensors you would study about. So, what is the task of robotic intelligence? Construction of a model of external world, integration of sensory data in that model to lead to a final model with no confusions, no conflicts, and consequent reasoning and decision making, which way to go, how to go, and so on. Vision is a part of this course in which you will study extraction, characterization, and interpretation of information from 2D images of a 3D world. How the scenario may be, so that you get from pictures which the robot's camera or the overhead camera taking pictures for all generates in 2D. So, what would you think as a perfect robot, as originally, conceived by the science fiction? So, it would be equipped with very good sensors and vision, which can operate at least up to the human smartness, and capable of working in unstructured environment. That is, where a hammer is expected, a hammer is not there, but there are other heavy things. Okay. Able to handle rapid and unexpected changes in scenario with fault tolerance and decision making capability. That is, the situation is not as expected, even in broad terms. Now, what to do? So, it should be able to do it and still accomplish the task. Or if the task is no more possible to accomplish, then it should be able to find it out and inform accordingly, a contingency decision, whatever. Okay. According to its environment, should be adaptable, and it should get stopped only when the task commanded is not possible to operate, perform. Okay. With why it is not possible and what should be done, what can be done. I mean, this is a tall order. Okay. But who knows what science and technology cannot achieve. So this is what in every scientific and technological advance, uh, people try to make one more step towards that. And when people will be satisfied, perhaps people will never be satisfied. Nobody knows. Okay? So this is the sense of what you could think of expecting from a robot. So I think this is where we can stop. And from the next lecture, we will go um, directly into how to represent robotic um, elements, links, and their connections, and so on, how to mathematically represent their mechanical motion, and so on. So, on that, the disciplined down to earth groundwork, we will start from the next lecture. Okay, and after that, on that, sometime in the coming days, I will upload that lecture, and after that, on Wednesday, we will have a suitable time to have our discussion session, and for that we have to discuss also, but that I will do in the forum or through email. Okay, thank you for today.